Hello, this is Dr. Hanaa Assil, and today we're talking about oxidation reduction reactions. So this is the third chapter in Unit 2 of the IAS Chemistry Edexcel. If you remember from the O-level, we had definitions of oxidation and reduction and redox reactions. We had several definitions actually for each one, but the one that we care about this year is the definition regarding transfer of electrons. So remember that oxidation reactions involve loss of electrons. So if sodium loses its outermost electron and becomes Na+, that is oxidation. Reduction involves gain of electrons. So chlorine atom, when it gains an electron, becomes Cl-. That is reduction. Redox reactions involve both oxidation and reduction. So in this reaction, for example, what happened is the iron lost electrons and became iron 2+. That is oxidation. The copper 2+ gained 2 electrons and became copper, so that is reduction. So we can divide an oxidation reduction reaction into what we call two half equations. One in which oxidation is happening, one in which reduction is happening, and the overall equation is the addition of both. So if we have any oxidation reduction reaction, first of all, we said there is an oxidizing agent and there is a reducing agent, and we said the oxidizing agent is the substance that was reduced and the reducing agent is the one that was oxidized. Now you need to know examples of oxidizing agents. So if we're trying to oxidize something, I should add, for example, potassium manganate. And you should remember from O-level that potassium manganate is originally purple. If it reacts, then it turns from purple to colorless. Now, potassium manganate is an oxidizing agent, and that means that anything it is reacting with is a reducing agent. Now, another example of oxidizing agent was potassium dichromate. And we know from O-level that potassium dichromate originally is orange. When it reacts, it turns to green. Another example of oxidizing agents is halogens, and that is because halogens usually tend to gain electrons, and that means they cause whatever they're reacting with to become oxidized, so they are oxidizing. A reducing agent, as we said, is the substance that was oxidized. Now, if he says, give examples of reducing agents, well, we said we can react something with hydrogen, it will reduce it, or carbon monoxide, or metals, because metals tend to lose electrons, so they give electrons to what is in reacting with them, so they are causing that substance to be reduced, so they're acting as reducing agents. Are we following all of this so far? So from all of this is from O-level. We said if I have a reaction like that first reaction, now the copper oxide changed to copper, and that means it was reduced. So the reduction reaction is the reaction between copper oxide to give copper, hydrogen to give water. That is oxidation. And we said the one that was reduced, that is the oxidizing agent. The one that was oxidized, that is the reducing agent. So that is from the O-level. Now, when we talk about transfer of electrons, well, what happened to the iron? It lost electrons, so that is oxidation. Copper 2+ gained electrons, so that is reduction. And the one that was oxidized, that is my reducing agent. And the one that was reduced, that is my oxidizing agent. Okay, so far? Then we go into balancing of ionic half reactions. So if we have a reaction, we're supposed to balance it. So for example, I have this. So this is actually a reaction between iron 3+ and nickel. And it is supposed to give iron 2+ plus nickel 2+. And when we divide them into two, the iron 3+ gains electrons, becomes iron 2+. The nickel is the one that loses electrons and becomes nickel 2 plus. Now, in order to balance this equation, what he will tell you to do is write the overall ionic equation. To write the overall ionic equation, the first thing would be try to make the electrons lost and gained to be equal. So if you look at that first equation, it is gaining 1 electron. But the second equation says we need to lose 2 electrons. Now we need to make the number of electrons equal. Now what can I do to that first reaction so that the number of electrons on both sides would be the same? Well, I can just multiply by 2. So that will be 2 Fe3 plus 2 electrons, 2 Fe2 plus. So you multiply all through by 2. Now that means that my number of electrons are equal on both sides of the arrow. I can cancel the electrons and add up everything on either side of the arrow. So if I cancel the 2 electrons, that means I'm left with 2 Fe3 plus nickel before the arrow, and I'm left with 2 Fe2 plus nickel 2 plus on the after the arrow, and that is what we call the overall reaction. Are we following here? So let's try it with this one. If we say we have these two equations, one of them is oxidation and one of them is reduction, we need to write the overall equation. So what we need to do first is to balance the equations. And when we balance ionic equations, remember, we balance the number of atoms first and then the number of charges. So that first equation up there, what I need to do first is balance the number of atoms. So before the arrow, I have 2 chromium. That means I need 2 chromium after the arrow. Before the arrow, I have 7 oxygens. So I need 7 oxygens after the arrow. How many hydrogens now do I have? After the arrow, I have 2 times 7. 14. That means I need 14 hydrogens before the arrow. So now I have balanced the atoms. Now I need to look at the charges. How many positives and negatives on either side? If you look at after the arrow I have 2 times 3. So I have 6 positives after the arrow. That means I need to fix what is before the arrow so that I have a total of 6 positives. Remember that the charges should be equal on both sides of the arrow, or if it is 0 on one side, then it must be 0 on the other. So they have to be equal on both sides of the arrow. So what can I do? I can say I have 6 electrons. Now remember that the dichromate, the Cr2O7, has 2 negatives. I have 14 positives, so 14 minus 2, that is 12. So if I put 6 negatives, 6 electrons, that is 12 minus 6. So my overall before the arrow is 6 positives. And the overall after the arrow is also 6 positives. So that part of the equation is balanced. Let us look at the second equation. The second equation, we need to balance atoms and we need to balance charges. So let's take a look at the atoms. We have 2 carbons before the arrow. We have 2 carbons before the arrow. We have how many carbons after the arrow? We have 2. We have 6 hydrogens plus 2, that's 8 before the arrow. Now after the arrow, I have 3 and 4. 3 and 1, that's 4. So I need 4 H pluses to have 8 hydrogens on both sides of the atom. Now the atoms are balanced. I need to balance the charges. So after the arrow, how many charges do I have? First of all, before the arrow, there are no charges at all. So that means the total should be 0. Now after the arrow, I want also the total to be 0. So if I have 4 positives, then I have 4 negatives so that they are 0. Okay, now I have balanced each half equation. Now I need to look at the number of electrons in each equation. So the first equation has 6 electrons before the arrow. The second equation has 4 electrons after the arrow. Now what can I do to each of these equations so that both of them will have the same number of electrons? Well, let's see. 4 and 6, I can try to make each of them to be 12. So I can multiply the one on top. all through by 2. Remember, if you multiply by 2, you're not only multiplying the electrons, you're multiplying everything. So, and the one down, I can multiply all through by 3. In that case, that will make 12 electrons for each one. And that means I will have that equation that I have just written in blue. So I have 12 electrons here. The other one I'm multiplying by 3, all through by 3. So I still have now 12 electrons. Now I can cancel the electrons on both sides of the arrow, and I add up the equations. Remember that if you have something on both sides of the arrow, then you subtract them. For example, I have 28H plus up there, and I have 12H plus on the other side in the second equation. So 28 minus 12, I end up with 16H plus before the arrow. The water, the first equation has 14 water after the arrow. The second equation has 3 water before the arrow. I subtract them, I end up with 11 water after the arrow. Otherwise, you just add up everything. So that last equation is my overall ionic equation. Are we all following this? This is very important. Let's try this one. I have the first equation and the second equation, and we said we want the overall equation, and that means the first thing I should do is balance the atoms in each equation, balance the charges, and then I try to make the electrons the same. So let's try and do it. That first equation, before the arrow I have 1 manganese, after the arrow 1 manganese. Before the arrow I have 4 oxygens, so I need 4 oxygens after the arrow. That now makes 8 hydrogens after the arrow. That means I need 8. Now I need to balance the charges. Well, as you see, after the arrow I have 2 positives, and that means the total before the arrow should also be 2 positives. So what do I have? I have 1 negative on the manganese, 8 plus, so that means 7 plus. In order to have a total of 2 pluses, I should have 5 electrons. The second equation, let's balance the atoms. Before the arrow, I have 2 hydrogens, so I need 2 hydrogens after the arrow. Before the arrow, I have 2 oxygens. After the arrow, I have 2 oxygens, so that is balanced. Now I need to balance the charges. Well, before the arrow, there are no charges at all, so the overall is 0. And that means after the arrow, the overall also should be 0. If I have 2 positives, then I need 2 electrons. Then I look at the number of electrons in both equations. One of them has 5, the other one has 2. I need to multiply each equation by something to make the number of electrons the same. So what can I do? I can multiply the lower one with 5. So that would mean that I have all of this multiplied by 5, and I end up with 10 electrons. And I can multiply the one on top by 2, so that I have all of these, and I have 10 electrons. Now I can cancel the electrons on both sides of the arrow, add up everything. Remember that I have 16H plus above before the arrow. I have 10H plus below after the arrow. I need to subtract them, and I'm left with 6H plus before the arrow, and bring down everything that we have. Are we following how to balance ionic half equations? Remember that each of these is actually an oxidation reduction reaction. So these are ionic half equations for oxidation reduction reactions. The next thing in the AS, and this is the new part in the AS, that we need to calculate the oxidation number of each of them. If you remember, in the O level, we said the oxidation number is actually the indicator of telling me how much oxidation or how much reduction has happened. And we said it is usually the charge if we have a charged element. That's what we said in the O level. But now we need to have more rules to assign oxidation numbers to anything that I have. So the first rule, let's go through the rules one by one to understand. To determine the oxidation number of something. First of all, if I have a molecule that is neutral, that means a molecule that doesn't have a charge on it. So I have a molecule like NaCl or something, no positive or negative on the whole molecule, then the sum of the oxidation number of all its atoms is regarded as zero. So if I have a neutral atom, the total oxidation number of that neutral atom is zero. If I have an element, the oxidation number of the element is zero. So if he says, what is the oxidation number of nitrogen? Alone, it's zero. Oxygen, zero. Hydrogen, zero, and so on. So oxidation numbers of neutral molecules, total zero. Oxidation number of an element is zero. Then another basic rule. Now, if we look at the periodic table, anything in group 1, I will give it an oxidation number of +1. So if I have a molecule or a compound and I have something from group 1, the one from group 1 will have oxidation number +1. Anything from group 2 will have oxidation number +2. Anything from group 3 will have oxidation number +3. These do not change. Anything in group 0 will also be 0. But other elements would change. So let us pay attention to this. If I have potassium bromide, for example, what would be the oxidation number of potassium and the oxidation number of bromine? The total should be 0. We said a total of any molecule is 0. So if potassium is in group 1, potassium has to be +1, that means my Br has to be -1. Again, I'm emphasizing, anything in group 1, 2, 3, 0 do not change. But all the other elements in the other groups could have different oxidation numbers. So the Br is in group 7. Remember that in the O level we said it's in group 7, so it needs 1 electron, so it has to be -1. Here, actually, it doesn't have to be -1. It could be -1 or it could be something else, and we'll talk about that in a minute. But here, in KBr, the total is 0. The K has to be +1. So in order to have a total 0, the Br is -1. The same for magnesium oxide. Magnesium is in group 2, its oxidation number is +2. And for everything to be 0, the total to be 0, that means that the oxygen is -2. I'm going to remind you again that when we write any oxidation numbers, we mean one of them, one of the elements. So if you have more than one element in a compound, you're writing the oxidation number of one. Okay, let's continue. Oxidation number of hydrogen is usually +1. So oxidation number of hydrogen is usually +1. So let us say I have HCl. HCl total is 0. So hydrogen is +1, then chlorine is -1. Water, hydrogen is +1. Each hydrogen in water is +1. Again, the oxidation number is for one of them. So each hydrogen is +1. That means the total for 2 hydrogens is +2. So the oxygen is -2. So remember that hydrogen is usually +1. But there are exceptions. Now, when do we have an exception? If the hydrogen is with something metal in group 1 or 2 or 3. Remember that we said a metal in group 1, like sodium, its oxidation number has to be +1. So you can't have two things that are +1. If I'm saying that hydrogen is usually +1, if it is with sodium, it is the sodium that has to be +1, and that means the hydrogen will be -1, so that the total oxidation number is 0. So hydrogen is usually +1, except in certain cases where it is with a metal. If it's with a metal in group 1, 2, or 3, then it becomes -1. So MgH2, again, MgH2 total, this is a neutral molecule, so the total has to be 0. But we said magnesium is in group 2, so magnesium has to be +2. So each of these hydrogens has to be a -1, so that +2 -2 will be 0. Paying attention, whatever oxidation number we write is for one of them. So I don't say that H2 is -2. No, I'm talking about the oxidation number of each of the hydrogens. Again, another rule is oxidation number of oxygen is usually -2. Oxidation number of oxygen is -2. So if I have, for example, carbon dioxide. Carbon dioxide is something that has one carbon and two oxygens. So each of the oxygens, if each of the oxygens is -2, then this carbon has an oxidation number of +4. Because +4 or -4, then the overall is 0. So oxygen is usually -2. Except there are some exceptions. What if we say, what is the oxidation number of oxygen in hydrogen peroxide? Hydrogen peroxide is H2O2. It is a neutral molecule, so the total oxidation number should be 0. So what is the oxidation number of each oxygen? Well, each hydrogen we said is usually +1. Remember, we said hydrogen is +1 unless if it is with a metal from group 1, 2, or 3. Otherwise, it's +1. If I have two hydrogens, each of them is +1. And that means to have a total of 0, then the two oxygens have to be -2. So each of them will have an oxidation number of -2. The oxidation number of oxygen is usually -2, except in peroxides, it is -1. Again, if I have sodium peroxide, this is the same. Sodium peroxide, it's a neutral molecule. The total is 0. If each sodium is +1, then the oxygen, each oxygen should be -1. Okay. Another exception is in what we call superoxides. Now, we know that group 1 form more than one type of oxide, or we're going to study that in a later chapter. So we have something called potassium superoxide. This is a neutral molecule, so the total should be 0. But then potassium is in group 1, and we said the potassium has to be +1. And that means the two oxygens have to be -1. And that means each one will have an oxidation number of what? An oxidation number of -12. Are we paying attention? So in peroxides, the oxidation number of oxygen is -1. In superoxides, the oxidation number of oxygen is -12. In OF2, again, let's look at OF2. The total oxidation number is 0. Now, we were saying up there that the oxidation number of oxygen is -2. But if it is with fluorine, which one is more electronegative? You should realize that fluorine is more electronegative, so it is the fluorine that should be minus, and that means the oxygen has to be plus. So in this case, each fluorine is -1, then in this case, the oxidation number of oxygen has to be +2 in order to have a total of 0. Are we following? So this means oxidation number of oxygen is usually -2, except in peroxides it's -1, in superoxides it's -12, and when it is bonded to fluorine, then it is +2. Okay, another rule. What if we don't have a neutral molecule? We have what we call an atomic group. You remember what's an atomic group? Carbonate, nitrate, sulfate, and so on. First of all, the sum of that group is equal to the charge. So for example, if I have nitrate, if you remember, nitrate has to be written NO3 minus. So the overall charge on the NO3 is -1, and that means the total oxidation number of this group is -1, not 0 as what we said. We said if it is neutral and there is no charge on top of it, then the total has to be 0. But here there is a charge. That is the total oxidation number. So the total oxidation number for nitrate has to be -1. And that means if we say that each oxygen has an oxidation number of -2, remember, we said oxygen is -2 except in the specific exceptions that we mentioned. So otherwise, oxygen is -2. I have 3 of them, so that means the oxidation number is -6 for the oxygen. The total oxidation number for the 3 oxygens is -6. Now, what would be the oxidation number of nitrogen so that the total is -1? So the nitrogen here has to be +5 so that overall there is a charge of -1. Again, if I'm talking about carbonate, the total oxidation number for carbonate, remember the carbonate was CO3, 2 minus, that means the total is -2. Now, the oxygen, each of them is -2. I have 3 of them, so that's -6. So again, the carbon has to be what? The carbon has to be +4, so that overall I have a 2 minus on the carbonate. The same for sulfate. The total oxidation number is -2. The oxygen, each of them is -2. I have 4 of them, that's -8. So the sulfur has to be +6 in order to have a total of -2. Ammonium has a +1 on it. So the total oxidation number is +1. If hydrogen, each of them is +1, that means I have +4. Then the nitrogen has to be -3 so that the total is +1. I hope you're all following all of this. Now, another rule. Remember that we said group 1, 2, and 3 have a specific oxidation number, 1, 2, and 3. But we said the rest of the groups, you can have variable oxidation numbers. And remember that the lowest possible oxidation number is the group number -8. So if I'm talking about nitrogen, nitrogen is in group 5. So the lowest oxidation number it can have is 5 minus 8. So that is -3. And the highest oxidation number is the number of the group. So if this is group 5, then the highest oxidation number is +5. So let us take a look at all of these molecules that include nitrogen. If I have NH3, again, each hydrogen is +1. I have 3 of them, that's +3. The overall should be 0, so the nitrogen in that case is -3. What about N2? Remember we said oxidation number of an element is 0. N2O, each oxygen is -2. The overall has to be 0. So each nitrogen is what? +1. If I have NO, the oxygen is -2. The nitrogen has to be +2. If I have N2O3, each oxygen is -2, so I have -6. So each nitrogen is +3. NO2 is +4. N2O5 is +5. So notice again, for groups 5 or 6 or 7, the lowest oxidation number is the group number -8. So group number 5 minus 8 is -3. And this is usually the hydride. So it's usually the element with hydrogen. Now the highest oxidation number is number of the group. This is something in group 5. So this is +5. Again, if we're looking at sulfur. So sulfur in this case is in group 6. So sulfur in H2S, well, each hydrogen is +2, so the S is -2. Again, that is the group number -8. So the group number is 6 minus 8, so the lowest oxidation number is -2. Sulfur standing alone as an element is 0. SCl2, Cl is usually -1, so I have 2 of them. That means the sulfur has to be +2. Oxygens, usually each of them is -2, so I have sulfur +4. Here, each oxygen is -2, so I have -6, so the sulfur is +6. So the lowest is the group number -8, 6 minus 8, that's -2, and the highest is the number of the group. This is in group 6. Are we following how we got the oxidation number of each one? Okay, let's do some questions. Determine the oxidation number of these species. So again, if we're looking at iodine, now I2 is an element. We said the oxidation number of the element is 0. Ki, we said potassium is in group 1. It has to be +1, so the iodine is -1. In KiO3, each oxygen is -2. I have 3 of them, that's -6. Now the positives, K is +1, so the iodine has to be +5 in order to have an overall oxidation number of 0. Okay, let's try that second equation. So F2 is an element, oxidation number 0. Now the OH minus, the overall has to be -1. Now if oxygen is -2 and H is +1, then the overall is -1. Okay, what about the F after the arrow? Well, the F minus has a total of -1, so its oxidation number is -1. Looking at the OF2, we said what happens in the OF2? We said if the oxygen is with a fluorine, the fluorine is more electronegative, so it is the fluorine that has to be -1, and that means I have 2 of them, so that's -2. So in this case, the oxygen is +2. Okay, remember, and this we said before in the O level, oxidation number, the oxidation, in any oxidation reactions, the oxidation number increases, and in any reduction reaction, the oxidation number decreases. Now, so far we have been talking about redox reactions, and we said redox reactions involve both oxidation and reduction. So one of them is reduced and the other is oxidized. There is one type of redox reactions which we call a disproportionation reaction. So remember that disproportionation reactions originally are oxidation reduction. But the difference between this and the normal redox reaction is that this disproportionation reaction involves an element in a certain reaction. Once it was oxidized and once it was reduced in the same reaction. Remember that in normal redox reactions, a certain species, copper 2 plus, for example, is reduced. That's it. The other species is oxidized. That's it. But in a disproportionation reaction, the same element is both oxidized and reduced in the same reaction. For example, let's take a look at this equation, and this is an equation that you need to know when we start talking about halogens. Now, this is a reaction of chlorine with sodium hydroxide. It gives NaCl plus H2O plus NaClO. So let us take a look at the oxidation number of chlorine in each of these elements. The first one, chlorine, is an element, so that's 0. Now, after the arrow, I have NaCl. Again, Na is in group 1, so it has to be +1, so chlorine is -1. What about in NaClO? Well, we said the O has to be -2. This Na has to be +1. So the chlorine in this case is +1. So notice that in the equation, what has happened to chlorine? First of all, we said an oxidation reaction is where oxidation number increases. A reduction reaction is where oxidation number decreases. So what has happened to the chlorine? It has changed from 0 to -1. Oxidation number decreased, that is reduction. But the same element chlorine has also changed from 0 to +1, and that is increase in oxidation number, and that is oxidation. So chlorine to NaCl, that is reduction. But chlorine to NaClO, that is oxidation. So in the same reaction, we have oxidation and reduction. This is an example of a disproportionation reaction. Let's try this one. This is another equation between chlorine and sodium hydroxide, but in this case it's giving sodium chloride plus water plus NaClO3. Again, what's the oxidation number of Cl2? 0. Now, NaCl, Na is +1, so Cl is -1. Now, NaClO3, each oxygen is -2, that means I have -6. Now, the Na is +1, so the chlorine has to be +5 in order to have an overall oxidation number of 0. This other equation also is another example of a disproportionation reaction. So I have chlorine plus water to give HCl plus HClO. Well, Oxidation number of chlorine in Cl2 is 0. Now in HCl, the hydrogen is +1, so the Cl is -1. Now in HClO, the hydrogen is +1, the oxygen is -2, so the chlorine has to be +1. So again, the chlorine changed from 0 to -1, reduction, from 0 to +1, oxidation. So this is a typical question on this. He's saying which of these is a disproportionation reaction? Well, let's see. We said, first of all, to be a disproportionation reaction, it has to be an oxidation reduction reaction. So something must be oxidized and something must be reduced. That first equation that says calcium carbonate changing to calcium oxide plus CO2, this is actually a thermal decomposition reaction. So that cannot be a disproportionation reaction. And if you sit down and calculate, for example, the oxidation number of calcium, it starts with +2, it ends with +2 also, so the calcium was not oxidized or reduced. Now let us look at that second equation. Well, I have H2O2 changing to water plus oxygen. So we said hydrogen peroxide, the oxidation number of oxygen. Hydrogen peroxide is -1 because the overall has to be 0 and each hydrogen is +1. So I'm starting with oxygen -1. Now what happened to it? It changed to water. In water, the oxidation number of oxygen is -2, plus O2, the oxidation number in an element is 0, and that means my oxygen changed from -1 to -2, that is reduction, and from -1 to 0, that is oxidation. So this is my example of disproportionation reaction. If you look at the other equations, they will not show you any change in oxidation number. So we're going to stop here. I hope this helps you to understand the chapter, and please listen to the next video, which will be discussing questions and answers on this chapter. Thank you for listening to these videos.